Hello everyone, welcome to another lecture. And this is the lecture number 4 of AI Embedded Systems. And today's lecture is about digital input and outputs. In this lecture, basically, I'm going to cover the parallel parts of a microcontroller and some registers associated to these ports, and how to configure a pin of a microcontroller to be set as a input to output, like general IOs, and some kind of a bit manipulation, which is dealing with the programming when you're using C programming, and a few example C codes written in Atmel Studio. All right, so in this lecture, so I take the example of Atmega 328 or 328P type of a microcontroller, which is the microcontroller using Arduino Uno or Nano boards. But this is a very advanced Atmega series microcontroller, low cost, but having many features. So as you can see, this is the microcontroller. It has this microcontroller has the footprint is 28 SPDIP, which is like a true hole type. You can easily plug into a breadboard because these true hole pads are there. And basically, not all the pins are accessible for general input and outputs. You can see like 28 pins. 4 of them are dedicated to power supply. This is VCCs. You should connect it to the 5-volt power supply, and ground is connected to the negative of the 5 volts power supply. And again, here is another ground for the analog ground. And a VCC is the analog supply voltage. Sometimes you can directly couple this AVCC and VCC and ground and this analog and digital ground. And A reference is a reference for the analog channel. So these 5 pins are dedicated for power supply and analog to digital conversion purposes. Other than that, you can use this rest of the pins for your any other applications to connect the sensors, LEDs, or any way of any method. All right. So these input and output pins, you can see like they are divided into several ports. Okay. For example, if we look at the port B, so starting with pin number 15, 16, 17, 18, 19, like pin number 15 is PB1, and pin number 14 is PB0, likewise like B0, B1, B2, B3, B4, and B5, and B6 and B7. Altogether, 8 pins are dedicated for port B. So the numbers like B represent the port B. Likewise, numbers with D represent the port D. Like any port most probably has 8 pins because this is an 8-bit microcontroller. So if you take any port B, so you might have 8 input and output pins. And port C also we having here PC7 is not present, but there are 7 pins. Likewise, a general port has 8 pins, right? Starting from 0 and ending with 7. Right. So these input and output pins, you can configure them as an input or output by writing to the relevant control registers by using your compiler. So these pins are called as digital pins. So they are bidirectional. You have the freedom to configure them as either input or output. Like I mentioned, they are 8-bit, 8 binary input-output pins. When you consider them together, we can call it as a port, right? So number of ports depend on the microcontroller type. Here we have 3 ports for B, C, and D. If you need more and more pins for, if your application is more complicated, you can buy a different microcontroller having many ports, many different ports available for your application. Okay, so these are general purpose input and output pins, but sometimes they can also do other purposes as well. If you take a look at this this port C, right? So port C, PC0 is a digital pin. Sometimes you can configure it as an analog pin, right? So we will discuss the analog ADC in later, but today's discussion is to use a digital input and output pin. So any port associated can be configured as a digital pin. But also remember they can support different other purposes as well, like analog to digital conversions for counters and etc. Right. So if you take a look at this a single pin, like if I take single pin here, pin number 15, let's take. So this is that pin. So this is what is exported to the whole outside world from here. This is your outside. These things are inside to the microcontroller, right? Everything from here is inside to the microcontroller. You can't see them. You can only see this pin. So this is a pin that you have the access. Okay. So any pin, any ports has a read, modify, write functionality when use them as a general digital input and output. So you can configure it as a to read the data, and sometimes you can configure them as to read the data or write data to these pins. The direction of one port pin can be changed without unintentionally changing the direction of any other pin. So which means like if you consider the single pin, right? So you can change it as a input while keeping all the others as output. Or you can set it as the output while keeping all the others as input to output, right? Without changing the configuration of other things, you can just configure single pin, right? So you don't need to change the whole port pins altogether. You can change one single pin to one direction, this other pin to another direction. Likewise, you have the freedom to change anything. And also, if you set it as an output, you can either configure it to drive the current or sink the current. So this, when it's set as a driving, you can simply drive a simple LED connected to this pin. That is enough to drive a simple LED light. Okay, so likewise, you can configure it as output, or sometimes you can configure it as a input, which means like you can connect it to a sensor. So that sensor output pin maybe like a temperature reading coming from this pin. You can connect it to this pin and read that data. Or maybe it could be either digital form. And here there's a pull-up resistor. I will tell you what is a pull-up resistor is. Like if you set this pull-up resistor, which means basically this is connected to the 5-volt supply, right? This diode and this diode. So when you set this pull-up resistor, this transistor will short circuit, and this 5-volt will be appear in this pin, right? So if you enable this pull-up resistor, if you measure from a voltmeter, you will see there's a 5 volt applied on this pin, right? Which means this is a short circuit in this transistor and put up resistor driving this pin to 5 volt because there's no current following. V is equals to IR. This voltage drop will be 0 and this voltage drop will be 0. The 5 volt will appear in this pin. So normally we don't use pull-up resistor in many applications, but if you want, you can enable them. And the diodes here, they serve it for protection purposes. For example, now assume like the microcontroller works with 5 volt supply, right? Sometimes now you connect it to a sensor or like a whatever the reading comes as a digital signal, like 5 volt and 0 volt. Okay. Sometimes due to some external effects or switching of inductive loads or something, there could be some spikes on top of this waveform. Like this could reach up to 6 volt, right? Due to some noise or any kind of like a external effects. This is not like a nice and clean 5 volt. Instead, it could have some kind of bumps. Like that voltage could rise to 6 volt. Okay, so if 6 volt comes here and this voltage is 5 volt, so we have to anyhow protect this pin somehow without exceeding the maximum absolute maximum value rating of this pin. So typically any pin can like tolerate 5 volt plus or minus 0.5 volt. Okay, so 5.5 will be acceptable, right? So now 6 volt comes, so that is not good for this port, right? So potentially it could damage. In that case, you can see like this is 6 volt and this is 5 volt. Now this diode can forward bias because this side has the highest voltage and this side has the lowest voltage. So this diode will allow to current to flow to this 5 volt channel. And so now you know like when this diode is forward bias, maybe if it is like a Schottky diode, there's only like a 0.3 volt drop, right? So now you know this voltage is 5 and there's a drop of 0.3. Now this voltage should be exactly around like 5.3, right? 5.3. 5.3 volts, right? So that is safe. So this 6 volt, like that was coming from here, somehow like when you short allowing this diode to happen, so this voltage must be dropped to 5.3. So 6 volt here. So somehow like that the rest of the voltage, maybe this is less than 6 volt. When you don't have this diode conducting, all the 6 volt appearing here. Now, when you allow this diode to conduct, this is 6 volt and the rest of the voltage will be dropped across these PCB traces, along the PCB traces, right? And all the junctions. So this port or this pin will be safe, right? So this is 5 and this is 0.3 and this diode is conducting, allowing this high voltage to pass through this diode. And this is 5.3. which is lower than the maximum allowable voltage of the diode, right? So that is the purpose of having this upper diode, right? Otherwise, like they don't put these diodes there. That's the main purpose to suppress high voltages. And also, like I mentioned, sometimes you have 5 volt, sometimes you have 0 volt, like this is digital. Assuming this is a 5 volt microcontroller, this should be 0 volt, but due to some surges, this could have also some bumps, right? Now this voltage could go up to like a negative voltage, negative -1, right? Due to some kind of like a inductive switching or something. So it should be nice and clean 0 volt, but we can't predict. Due to some sort of external effect, the voltage could drop to -1. But the lowest voltage allowable will be 0 minus 0.5. So it is typically minus 0.5 volt. So if you exceed more than minus 0.5, this pin will be damaged, right? So if you can see here now, this is -1. This diode is connected to the ground internally. All things are internal to the micro. Right, 0 volt here, -1 here. You know, like this diode can conduct because 0 is higher than -1. So the current can just pass through this diode and forward bias it and allowing the current to flow through this diode, right? So it's similar to previous case, we can consider this voltage drop as 0.3, typical Schottky diode voltage drop. So in that case, this voltage drop might be minus 0.3. Okay, so which means it doesn't exceed minus 0.5. So this pin will be safe. Whatever the extra voltage will be dropped inside this PCB traces, and likewise like -1 will be here, and the rest of the voltage -0.7 will be dropped across this PCB traces. So that's how the lower diode will protect the microcontroller from negative voltages. And there is some capacitance here, parasitic capacitance. That is not what they have put, but it is due to the nature of the microcontroller. You can't avoid it. It is in the range of picofarad range. Sometimes it is troubleshooting when you're driving high, your digital signals are very high frequency. Then this effect of this capacitor will be critical. So other than that, there's nothing to worry about these capacitors. And the term tri-stated, sometimes you will see in the datasheet of, if you download the microcontroller datasheet, sometimes they refer it as tri-stated, which means this pin this port act as a high impedance, which means like this side, if someone looks, it will show it as like an infinite impedance, like a open circuit, right? So someone measuring the resistance from this side, he will observe it as like infinite resistance, which means like this impedance from here, seen the impedance is infinite, right? Infinite impedance is ideal case. For example, now it is not natural, but there could be infinite is the ideal case, but maybe 1 mega ohm impedance, right? So if you're having some kind of like a sensors or anything you connected here, when you're having high impedance, which means like if it is a 5 volt signal comes here, and only a very short low current will be flown through this resistor due to high impedance, and there won't be any drop in this voltage, right? If it is 5, it will be 5. And if you're having low impedance, like let's say 100 ohms or something, definitely this 5 volt will be dropped to like a 3 volt or something. It is not desirable, right? So keeping high impedance is very much critical when you connecting sensors to these input channels. Right. So like I mentioned, these pins can be configured as an input to output. So that has to be, you can't do it hardware, right? So you have to deal with by these microcontroller registers when you program it. So there are, if you take a single port like port B, so there are 3 basic registers in the microcontroller. Register is something like some kind of like 8-bit or byte. So you can write value to that byte. So that is what called it as a register. So 3 registers are there: DDRX, and pin X and port X, right? So TDRX refers to data direction register. So that is a read-write register, which means you can either write value to it or you can read the value written already to this register, right? And data register port X, this is the one. So it is also read-write. So when you set it as an output, you can write it as to push the current or sink the current, right? For example, if you want to drive a LED, you can just write it as 1, so the LED will be driven. If you want to sink the current to the port, you can write it as 0. And pin X is a port input pin. So once you configure it as this port as an input, you can read the value to what is coming to this pin, right? So the port value can be read from here. The port value can be write from here. The port direction, like whether it is input to output, can be changed from data direction registers. So 3 registers are really important. And also, most cases, you don't need to have this pull-up resistor. So by default, we have to disable this pull-up disable PUD bit in MCUCR register should be disabled to this with by writing to digital high to this bit, right? PUD bit, because most of the time we don't need this one, right? So this is that MCUCR register. This is how it looks like. It has 8 bits. All of some of them are read-write and some of them are read-only. And these read-only things are like there's nothing here, so you don't need to deal with them. So this is the PUD register bit, right? So pull-up disable. So if you want to disable that pull-up registers, all you need to do is so you have to write 1, right? So initial value will be 0, which means like when you buy this microcontroller from the market, it has like a 0, right? 0 is written. But if you want to disable it, you have to write the value 1 in program. So you have to write 1 to this register and to this only for this bit number 4. Then all the pull-up resistors will be disabled in all IO ports, right? So it is very easy. And these are the other registers that I have just discussed. If you take for individual ports, there are different like dedicated registers. DDR-B represent for port B. So if you want to do something to port A, you have to deal with port A register, right? Not for port B. So TDR is data direction register of port B. This is it, how it looks like. It's an 8-bit register. All of them are read-write. So initial value is 0, which means like all of them are set to as input, right? If you want to set this pin to output, you have to write digital 1 to this pin, right? If you keep it as 0, it will be an input pin. If you set 1, it will be an output pin. And port B data register is something like to write the value to that register. For example, now you set this as DDR-B, you set it as 1, which means you want to have like this is the microcontroller, right? And so port B, RB, let's say RB3. So you want to drive a LED, right, from the same. So you connect a resistor and a LED, and you connect it to the ground. Now, like default, it comes as 0, which means like it's a high impedance, nothing will happen. So if you want to drive this, you have to first set it as an output, because you are driving current from the microcontroller to the outside world, right? So you are not reading any value. You just want to drive something or sync something, right? So you have to first go to the DDRB and write digital 1 to this pin, DDRB3. So then you set it as output. But still you won't see this LED will be light up, right? Because the value of port B3 is 0, which means now it is an output port, but the value 0 is written. 0 means like there's no voltage, right? So now what you need to, if you want to drive this LED, you go and just write 1, right? Which means now this is digital 1, which means this point will be 5 volt now, right? Now 5 volt will appear, and some sort of this resistor is to limit the current through the LED, otherwise the large current will flow. And now the LED will be light up. Otherwise, it will be off even though you set it as output. And that is the way that you configure it as an as output. Sometimes you need to use a microcontroller to read some data from a sensor, like a microcontroller is here. Now take a look at now like RB2 pin. So there's a sensor device is connected here, right? S1 sensor is connected and it is sharing the common ground. This is common ground. Now S1 is generating 5 volt, right? And 0 volt sometimes. So you have to check whether what is the voltage coming from this sensor, right? So definitely it should be like a input, because you are reading something. You are not driving this sensor. You just want to check whether what is the sensor value, right? So you are reading. So first you have to configure this port RB2 as the input. So you go here, RB2, and go to DDRB and select RB2. And now it is input, right? Already input, because the 0 is written. Or sometimes if you can just overwritten it as a 0 again, right? Doesn't matter. So you write 0 here. So it will be act as an input. So it is high impedance from this side. And so you don't need to write anything, because we are not driving. So you don't need to worry about port B, right? So all you need to do is just read the value from here. So you go to pin B to here, and you just read the value of request what is the current value of pin B2. So if it is 5 volt from the sensor, you will see it as a digital 1. If it is 0, you will see it as a 0, right? So this is how you deal with these registers in Atmel Studio. But if you use Arduino high-level languages, you don't need to deal with these registers. It is done by the compiler, right? That is why the Arduino is most famous, because any user, like anyone who is using the Arduino, doesn't need to worry about anything. He just has to write some kind of like a simple line and get the data to that pin, or write the data to that pin, right? That's why even like a O-level student can understand Arduino. But when you go for industry, when you developing products, the Arduinos are too simple, right? So more complicated things cannot be done. Sometimes it is possible. Sometimes if you have a customized product, and if you are worried about the cost and size, because like Arduino, even if you select the nano board, it will be something like this, right? with the USB port or something, right? So you can't plug Arduinos if you are designing like a very small, tiny, like a very small sensoring device. The size is critical. You can't place this Arduino inside this box, right? This is your sensor. So most of the cases, if the companies are like will use like a very small microcontrollers, like size will be like this, right? Very tiny microcontrollers. And so there will be more other electronics devices. So the capacitors and like that. So in that case, several companies are rely on dedicated microcontrollers rather than Arduino. So if you get a job, most probably you have to deal with all these things, right? You have to have some understanding. But if you learn all these things and if you work for a company doing Arduino, it will be easy for you, right? But if you learn Arduino and then going to a job who is dealing with microcontroller without learning this, the life will be hard for you. All right, so now you understand the purpose of these 3 registers, and we can think about configuring, learn about how to configure a pin. So here, if you want to configure any particular pin of a port, what you need to do is just go to the DDR register. So DDR-XN means like X is for DDR which port, right? N is the bit, which bit like it has like a 8 pins. So any pin has a particular bit. So this is the port and this is the bit. So the DDR-X register, X is for the port, A, B, or C, D. So that's the direction of this pin. Either if you write to that DDR-X pin, like I mentioned, right, 0 or 1, you can configure it as an input or output, right? So if you want to set it as an output, you have to write it as 1. Right? So if you write logic 1, the pin is configured as output. If you write 0, the pin is configured as an input. And if port XN is written logic 1, so any port and the N is the bit written logic 1, that pin is configured as an output pin. The port will be driven high, like you can drive current from this port, right? You can drive a simple LED. If the port N is written 0, the pin is configured as the output pin and the port is driven low. You can sync the current. Syncing the current means like here driving the current sourcing means you can drive a simple LED. So when means like if this is let's say RB2, right? Port B 02, you set it as 1, so this LED will be high, right? And syncing is you can drive the current, like in that case you can connect this to 5 volt, and this is a resistor and this is the LED. You can connect it as in this configuration, right? So in the previous case, if you set it as high, like it will be 5 volt and not, this LED won't be driven. But if you now if you like write port B B2 as 0, so this voltage will be 0, which means like the 5 volt here. Now the current can flow from here to here. through this port to the ground. So this LED will be light up. So it is sinking the current in this direction. Previous case, it was sourcing the current, and now it is sinking the current. So both configurations are possible, sinking and sourcing the current, the way that you connect your output devices. Now, so if the port XN is written logic 1, so if you written it as logic 1, and if the pin is configured as an input, now like if you don't disable this pull-up resistor thing, like if you don't disable it, like when you get buy the microcontroller from the market, by default it comes as 0, right? Some applications you want to have this pull-up resistor, you want to pull this line or this pin to 5 volt by short circuiting this. For some applications, most of the time like I2C communication, two-wire communication. So you have to keep this pin as 5 volt. This is 5 volt. So you have to enable this pull-up resistor. So what you need to do is just you have to keep this. You should not disable this, right? Just keep it as default 0. Then you have to set this pin as a port is written logic 1. When the pin is configured as an input pin, the pull-up resistor is activated. So you have to write the logic 1 to the port X register, right? And you have to configure it as an input pin, right? So you just go here and configure it as a direction, set it as an input by making it as 0, and then write digital 1, logic 1 to RB2. I'm considering RB2. First you go to this direction register and make it as an input, write 0, and then you write digital 1 to RB2. Then this pull-up resistor will be activated. If you do so, when you use a multimeter and just check the voltage of this pin, you will see it as a 5 volt, right? If you do it correctly, then only you will see as this pin is default will come as 5 volt after do these settings, which means this transistor is short circuited. So now you will use this pull-up resistor. So the typical value is around like 20 kilo ohms. And this if you want to switch off these pull-up resistors, most probably you can just disable from the P from here. You can write 1 to here, so all the pull-up resistors will be disabled. Sometimes you need to have 1 or 2 pull-up resistors in some pins. So in that case, you can keep it as default 0. And if you want to disable this pull-up resistor, all you need to do is you have to now write logic 0. Earlier you write logic 1, now you write logic 0. And you have to configure this port as an output port. So then the pull-up will be disabled. Right. So this is the table that is shown in the data sheet. So I have just copy and paste it here. This is how it looks like. So DDRXN, when you write it as 1, so when you write the data direction register as 1, so that digital pin will be set as an output, right? It is very clear. If the data direction register of pin is set to 0, that pin acts as an input, right? It's very simple. Direction is 1, which means output. Direction is 0, which means the input. And now the other thing is, so when you write 1, so even though if you set it as output, still the voltage of that pin will be 0. Now if you write 1, that pin will be at 5 volt, which means it can drive the current from that port, right? So it can drive a simple LED. And if the port RX port this pin bit is set to 0, the output will be 0 volt, which means sink in the current, right? And no matter the value written in for pull-up resistors, either it is 1 or 0, still it will you can set it as 0 volt or 5 volt, right? This is very useful when you're blinking the LEDs. You are dealing with these two registers. And now in the case when you write 0, which means this pin as the input, and no matter what is the PUD value, right? If you write 0, which means you are not doing anything, that pin is act as a dry state, which means like high impedance pin, right? You set this as an input, so it can you can connect a sensor or something. So that pin is at high impedance. Input pin impedance is infinite. And so you disable this, you write 0 to here, right? By default it is 0, which means when you write digital 1 to that pin, the pull-up resistors will be enabled, right? But you have to, you should not disable the PUD. But if you disable the PUD, all the pull-ups are disabled from the PUD register. Then if you write 1, nothing will happen, right? The pull-ups will not be enabled because pull-ups are disabled. All the pull-up registers are disabled for the microcontroller. Still, that's a high impedance pin, right? Now, if you want to read any value to a pin when it's set as an input, so you have to first set that pin as an input, writing 0 to DDRX pin. And now to read the value in that pin, you can request from pin X register that particular bit. If you read that pin X, so you can read the current value of that pin, right? No matter it is at the input, but it's still if it is output also, you can just read and verify the value written to that register. It doesn't need to be a input, right? It could be either input or output. Whatever the value in that pin, whether it is a 5 volt or 0 volt, you can read that voltage or logic value from pin X register. Now we are moving to the pull-up resistors and switches. Right. So sometimes you have to deal with the switches, which means you want to see, like if someone press this switch to do some activity, like if someone press this switch, like a turn on a LED or turn on a relay or turn on a motor or something, like, right? So you have to get some data from a user. So someone comes and press the switch, so the state or the voltage of this pin will be changed. That is why we're using these switches and pull-up resistors. Now, for example, let's see an example. You can use like a LED. This is a LED. So if someone press this switch, then only this LED should be light up, Otherwise, the LED should be off. Okay. So what you do is you have to compare this as an input, the voltage level. By default, you can add a pull-up resistor externally. You connect it to the 5 volt, and like if this pin is input pin, you have to configure it as an input pin, right? DDRX should be 0, and then it will be act as a input. And port X is also 0. So now, like, there's no current will flow, so this is at 5 volt, right? This hold the voltage because there's V is equals IR, and this impedance is infinite. Like I mentioned, there's a high impedance connected to the ground, and this resistance is like a very high, right? High impedance. So which means literally no current will flow. I is equals to 0. 0 into whatever the value you use here, the voltage drop will be 0 volt. Okay. So this voltage 0 and this is 5. And 5 minus 0, this pin, this voltage will be 5. Because like if you have a large resistor connected in series, the most of the voltage will drop across this bigger resistor, right? That's why when you measure from a multimeter, you will see 5 volt here. Then, now if you want to see that if someone press the switch, the pin voltage should be changed, right? Initially, it is at 5 volt. Now, assume the case like someone comes and press this switch. So he just pressed this switch and short circuiting, right? And we know there's a high impedance resistance here. This is infinite. So what is happening here is just you short circuit as a wire, and there's another infinite resistor. The parallel resistance, like a 0 parallel to infinite, will be 0, right? So allowing all the current to flow through this switch to the ground. And like a voltage drop across a piece of wire will be 0, right? So this voltage is 0. 5 volt will be dropped across this resistor, right? And you now will see like the voltage reading at this pin is 0, right? So earlier it was 5 volt, now it is 0. So you can write a code. Once it is pressed, you just keep seeing what is this voltage, right? Before pressing the switch, it was at 5 volt. After pressing, it is becomes 0 volt. So you can write a code like if the voltage changed to 0 volt, then light up the LED. Otherwise, the LED is off, right? So that is how you use these pull-up resistors and switches to get user input. And if you are too lazy to add like external resistor, and if you consider it as like for your PCB, you have to allocate more space, so you have to buy a resistor. So you don't need to worry about that. So all you need to do is you can use the internal pull-up resistor inside the microcontroller, right? It is easy way. In that case, if you enable this one, so by default, this pin will be at 5 volt, right? So you have to write to those registers to enable this pull-up resistor. Now you can simply connect some kind of like a switch, which is connected to the ground. So this is the pin, right? So, and you can just look at, you can just see and looking into what is this voltage, right? By default, it is 5 volt. If someone press this switch, the current will, this is connected to the 5 volt again, right? The current will be flown through this resistor, through the switch to the ground, and this voltage will be dropped to 0, right? The rest of the 5 volt will drop across the internal pull-up resistor. Now you definitely know someone has pressed this switch. Based on that, you can take a control action, right? So that is the importance of having internal pull-up resistors. You don't need to add external, you don't need to pay for external resistors, so you don't need to deal with the PCB layout because it is already available. And this pull-up resistor is voltage independence. Like if it is around 20 kilo ohm, and no matter like you use 4 volt or 5.5 volt, the resistance won't be changed. Like it is not someone like it is not the resistor that you see from the market, right? Like this kind of resistors you have seen from the market, right? Or this kind of like surface mount. Inside the microcontroller, nobody has put this resistor, right? It's like a silicon chip, and this resistor is like a silicon configured one, like a transistor, you know, like when you inside the microchip, like billions of transistors are there. Likewise, using the silicon, you can allocate a small area to make it as a resistor. It is not something someone has put inside, right? There is no way of doing that. So silicon resistor, but it is voltage independent, but there could be some fluctuations if the chip temperature goes high, the resistance could be changed slightly. But to many applications, it is acceptable. Now there's a pull down configuration as well. In the pull down configurations, by default, this switch is off, which means like this is at 0 volt. You know, like this resistor is connected to the ground. There won't be any current, like this is the input pin. This is like a high impedance resistor inside, infinite. Both resistors are connected parallel, and this is 0, and this should be 0 volt, right? What will happen is someone connect this switch, so the 5 volt now comes here, and it can go through this resistor as well as through this pull down resistor, making the equivalent, but you can consider it as an infinite, which means this is open circuit. Most of the current will go through the pull down resistor, and this is, you know, like the voltage drop across the switch will 0. 5 volt minus 0 will be 5 volt, so this will be 5 volt, right? So the state voltage change will be from 0 to 5 volt when someone presses the switch. So this is called as a pull down configuration. So your resistor is now connected to the ground. Pull up means your resistor is connected to the 5 volt supply, right? It could be external pull up or it could be internal pull up. Okay. And other thing is, practically the things are not the way that you expect, right? So if you press this switch, right? So now like this is a pull down configurations. So initially the voltage of this pin is at 0 volt, right? So if someone press this, the 5 volt will appear here. And if someone release again, so the voltage will be goes to 0. So ideally you expect something like this, right? 0 volt. Someone press the switch, it is 5 volt, and again it will be 0. But these switches are not ideal. They having some bouncing effect, like they having the springs and like that. So if you touch from your finger and release it, it could hit this for multiple times, like so the voltage fluctuation will be something like that. Sometimes it's 0 and it goes to maybe 4 volts and go down to 0 and again to 5 volt, again to 0 and then 5 volt, and then settle at 5 volt. And when you release it also, it goes to 0 and again jumps to 5 volt and to 0 and again 5 volt and then settling up to 0, right? So in the case, like if you just want to read how many times this switch is pressed, right? So if you write a code to read like how many times this switch is pressed by the user, you might see like in here it is 1 time, right? But in practically you will see like this, again you will consider it as a 1 because this came to from 0 to 5, right? Again 5. So 1, 2, 3. And so you will see like 3 times someone has pressed this switch, right? But he has only pressed 1 time. This is called bouncing effect. Okay, so if someone release it again, you will see like 0, 0, 0. 3 times someone has released it, but it is not the case, right? So this kind of bouncing effect troublesome in some applications. So mechanically you can't do anything. Means you can do something, but it will be complicated. Instead, you can wait for some time, like you can make a simple delay. Like if this hits 5 volt and just wait for some sort of delay and then wait and see if it is not going to 0. Then you definitely know if it is 5 volt. You know, like it's the same scenario. It is only someone has pressed it for 1 time, right? By using delays, you can get rid of this bouncing effect. And bouncing effect is real. I have seen it. So if your code is running too fast, you will end up with wrong values, right? You will see like the counter will be counted to 1, 2, 3, not as 1, right? So you have to think about that, and adding some delays, you can get rid of this bouncing effect. And so output loading, which means like I have already explained, if you want to drive a LED, there are 2 configurations. First one is you can connect the LED to the pin and through a resistor to the ground. Other way is to connect this LED to the 5 volt supply through a resistor to the pin, right? So they can drive, like any port pin can drive up to 40 milliamps, which is might be useful to drive a LED. But this current is not enough to drive relays, solenoid or motors, right? If you want to drive them, so you consider using transistors or relays or any kind of intermediate device, then passing that signal to drive the motors or solenoid or relays, right? Otherwise, you will burn up your port. So in this case, if it is 0 volt, nothing will happen. If it is 5 volt, the 5 volt will go through this diode and it will light up. Here, if you put 5 volt, here again 5 volt, no voltage difference, so the LED is off. If you put 0 volt, here again 5 volt power supply, and if you set 0 volt, now the current can go from the high voltage potential to the lowest through here and through the ground, right? So now the LED will be light up. And the thing is, somehow if you short circuit, like if you don't have this resistor or anything, like if you short circuit while having this, let's say, assume like this is a configuration. So now you drive it as 5 volt. So you just remove this LED and resistor and just short circuit, right? And sometimes that impedance is too much, too small, which means you are driving to the maximum potential or maximum current. Maybe that is if you drive it for too long, and that will potentially kill this channel pin, right? Or sometimes if you short circuit this pin to the ground somehow, like piece of wire, when it is 5 volt, you are literally short circuiting the port to the ground, right? Accidentally, if you do this thing also, the particular pin will be damaged. Most of probably what I have seen is if you damage a single pin in the port, like any port, like port D is here, it has like a 0 to up to 7, like 8 pins. If you damage the pin 0, the whole port will be useless, like all the other pins won't work, right? That is happening in the most cases. You can't use any other pins as well. If you kill the one pin, you will potentially kill in the whole the port, right? So that is why it is always recommended to use resistors and know your limits, like the maximum current is 40 milliamps. Based on that, use the value of the resistor for your application. It doesn't need to be a LED all the time. Sometimes it could be resistors only, or sometimes the sensors, or sometimes small transistors. So be careful when you're dealing driving from the output pin. Don't allow it to short circuit to drive any current more than 40 milliamps, so that potentially kill the pin. All right. Here, when you're writing the codes in Atmel Studio, it is sometimes convenient to use this kind of operations to deal with single bits rather than writing to the whole port, right? So the piece of codes written here will be for use of optimization, and it will reduce the memory, use of memory, rather than writing more and more lines and consuming the memory. Okay. So now let's say, like, as you know, like any port has 8 bits. If you want to clear single bit of that particular bit, so you have to deal with AND operations. So before that, let's take a look at the Boolean operation. So it is very simple. If you AND any bit with 0, like whether 0 and with 0 is 0, X is like either 1 or 0, right? So X and 0, when you AND with 0, the output will be 0. And if X AND with 1, you will get X, not the 1, right? Because if it is 1, you will get 1. If it is 0, you will get 0. And if you X or get with 0, you will get X. And if you X or with 1, you will always get 1. And if you do the XOR operation with X when you have 0, the output will be X. If you XOR X with 1, the output will be inverted of X. For example, now you XOR 1 with 0, the output will be 1. If you XOR 0 with 0, output will be 0. If you XOR 1 with 1, the output will be 0. If you XOR 0 with 1, the output will be 1. Okay. So if you want to clear the bit, single bit, you have to do AND that particular bit with 0 and all the other bits with 1. For example, now to clear bit 2 in port B, rather affecting all the other bits, now the current value is this one. The port B value is this, right? 0 1 0 1 1 0 1. This is the bit that I want to clear, right? So I don't want to change any other bits. So in that case, I can do AND port A with this bit sequence, right? So I will AND with this 0 with this 1, so it will be cleared, and I will AND all the other bits with 1. So if I AND with 0, I know like it will be, the output will be 0. If I AND with 1, The rest will be the whatever the value here, like I'm ending with 1 here, right? So ones and with X will be the same. So it doesn't affect the rest of the bits. So the code is like port A and equals. This sign is not setting the bit 2, right? This is like a bit 2 is set to 1, right? So bit 2, this is bit 2 set to 1 and take the invert of that, which means 0. So bit 2 is 0 and all the other bits will be 1 and you take the AND operation. So the output will be something like 0, 1, 0, 0, 1, 0, 1, 0, right? So each bit will be become 0. And if you want to set a single bit, you can have to do is like OR that bit with 1. For example, now you have the current value of this and you have to set that value. And now it is 0 and you have to set. So all you need to do is OR this bit with 1 and keep these other bits as 0, because when you OR that other bits, you will end up with the same value. So this is the code, like set bit 2 with 1, right? And the rest will be 0. You don't do anything. And then you take the OR operation for the whole for. Okay. And if you want to toggle a bit, like if it is 0, you can toggle it to 1. If it is 1, you can toggle it to 0. You can do it like just take XOR operation right in this code. And if you want to test a bit, like whether that bit is 1 or 0, you can write the code pin A. And for example, now I want to test bit 2. So I take like pin A and setting bit 2 to 1, right? This is that AND operation and set to 2. So you will get that value and you can do the AND operation. So it will be, you can testing that pin whether it is 1 or 0. Okay, so that is, we will do more example on this when we require, but just keep in mind, like this kind of codes you have, like lines you have to be remember and practice, right? And the logic will be something to deal with this table and the example that I have given. So you have to leisurely go through them and see how I have done it. Okay, right. Any programmer will start with a simple LED blinky code. So to blink a LED with a delay of 500 milliseconds. So you can write this code in Atmel Studio. Go and open the Atmel Studio and write this code. Before that, I will explain you what this code means. First, you have to define the CPU clock frequency, right? This is how you write in the program. Define F frequency CPU in hertz, right? And you will this term, you don't need to worry about that. So Atmega 328P comes with the internal RC oscillator with 8 megahertz. And with the fuse clock division 8 programmed, resulting 1 megahertz system clock. That is why I have used 1 megahertz rather than using 8 megahertz, right? Because if you use the internal clock, that frequency is 8 megahertz, you can use 8 megahertz, but make sure the register, this bit is unprogrammed. By default, this chip comes with this bit is programmed, which means this internal oscillator frequency is divided by 8, which is resulting 1 megahertz system clock. So this part I have just copied from the datasheet. If you copy, and you will find where this is written in the datasheet, right? So that is why I end up with 1 megahertz rather than 8 megahertz. So I'm using the internal oscillator, 8 megahertz, but since this bit is by default, it is programmed. when I buy from the market. So the resulting frequency is 1 megahertz. That is why my system frequency is 1 megahertz rather than 8 megahertz. Okay, so if you use external crystals or anything, you have to deal with these bits and make sure whatever the right frequency is used for the clock. Otherwise, your code won't be accurate. Then you can include this header, the library avr.io.h. And if you want to add a delay function, so delay is like a function defined from this library. So you have to include this utility delay.h library, then only you can use this delay function. And any code has a main function. This is the int main void, so it won't return, it won't accept anything, but it's returning integer, but we are not using that integer part, but this is your main function. And first line should be defining your port. So I want to blink all these LEDs like, so this is my port B, this is my Atmega chip. So this is port B. So RB0 and RB7. So everything is connected to LEDs, right? Through resistors. This one is again connected to the LED and resistors likewise. All the resistors are then connected to the ground. Okay, so so RP from RP0 to RB7, this is port port B. You have to set it as 1, right? So that register DDRB, you have to write 1, 6, 7, 8. This is which means like you know, this is DDRB register port B. So everything is output. So you have to write 1, right? For every bit you have to write 1. So in binary, you know, like all ones are 255, but in hexadecimal, it is FF, right? Either you can write it as there are possibility. You can still write it as DDRB is equals to 0 B 1 1 1 1 1 1 1 1, right? You can replace this line with this one also, right? Which means like you are asking to data direction register to make all the bits as 1 because you are using it as output. Or you can use this value as a hexadecimal, like 0xFF, double F, which means again equivalent to this number in binary, 255 in decimal. Okay. Right. Then this code will execute and comes with here. So here I have used a while loop. While one means it is infinite, so it is always true, right? Nothing will stop this loop. There's this condition is 1, which means true. This loop will run forever. So then the first line is port B equals to 0, which means like all the pins will be 0 initially, which means all the LEDs are off. So I'm writing the port B register now. Okay. So this is the port B register. So you have defined it as output. Now you write whether it is the output value as 5 volt or 0 or logic 1 or 0, right? So you have to write to port B register. So you define port B as 0 and make a delay 500 millisecond, half of a second. And then you write port B as all them of are 1. So all the LEDs will be light up and make a delay. Then again this code will compare this logic. The while one is again true, then comes and make it as 0, which means all the LEDs will be off, and wait for 500 milliseconds, and again make them all high and make 500 milliseconds. So you will see this, all the port LEDs will be blink in every 500 milliseconds, right? So you can represent this code or this as an algorithm in a structure diagram of flowchart. So this is the start, and then you initialize this everything, right? And then you defining this in your main function, port setting port B as the output. Then you go to a while loop, and then you may check the condition first. Check in this is not a do while loop, this is a simple while loop. So you check the condition first. If it is 1, then you will execute the rest and make the port B, set the port B output value as 0, and call the delay function. So this is calling the delay function from this header library. And again, then turn on the LEDs and call the delay function, right? Then again, go to the while loop and wait. Right, so this is how you develop your algorithm. Then you write your code. Okay. So this example is to blink LED in a port B, all the LEDs. And now this second example is to read a value from a port and copy the same value to the other port, right? Now I have used port B and port D. So start, right, port DDRB as 0, which means data direction is 0, which means port B is a input, and port D as an output, right? So then I goes to while loop and check this condition, and it is true always. Then I will copy whatever the value in port B is input and copy to the port D. Okay, so this is that code. DDRB is, you set port B as input and port D as output, and copy the port B value to read the port B. Pin B means read that port B and copy it to the port D, right? So application would be something like that. You have the microcontroller. This has a PBD, right? Sorry. You have your microcontroller, and this side is, let's say, 5, 6, 7, 8. RD0, RD7, and this side I have RB0 and RB7. So this is the input, and this is the output. So I can connect LEDs. Okay. Here. And I can connect them to some sort of switches, like this one. I can connect it to a switch. Right, when the default it is 5 and some are pressed, it is 0, right? Likewise, I can add another switch. This is the switch I'm connecting. So let's say like this one is pressed and this one is not pressed. So which means like this LED will be This is at 5 volt. This LED will be light up, and this is pressed, which means this is 0 volt, and this LED won't be light up, right? So whatever the value read from port B will be copied to the associated pin of the port D. So that's the meaning of this program. So that is all about this coding. So this is a very simple course. So you can try this in FL Studio. All you need to do is open the FL Studio and write this code by yourself. It is very easy. So I will demonstrate you how to do it. And I have also uploaded the getting started document PDF, so you can refer that and start writing this course. Okay. So this is how it looks like when you open. So all you need to do is just go to new project, open new project, and select this one, right? C++, and find this, rename it as like a Blink LED or something, right? And save it to the place that you like to save it in a folder, specify the folder. Then you have to select the device, the microcontroller. So here for this example, I have used Atmega 328. So you can find it from all this here, or you can search it 328. You can search it also, or else you can select the family Atmega and go down and see like through 328P is here, right? And press OK. Right, so this is how it looks like when you open it. So this is your main function. So this library is already included, and this is your while loop. This is a forever loop. So you have to write your code, and whatever you define, like port direction or any default things, you do it here and do it here. So now in this Blink example, now, so my CPU definition, so what I do is like I define my CPU here. If you want to add any comments, you can comment like this, right? Okay, just comment. That will be good practice. So anyone using it, you know what you have done, and without having this delay library, you can't use delay functions. So make sure you include this utility delay if you want to add delays in your code. And if you add this, make sure you have to define the clock frequency as well. Otherwise, it will give you some compilation errors. These two should go together. And so I can define in my port B as output here. So I set my port B as output. And so then I need to do is just add in this blink function. So I set the port P. Port P is the output now. So I write the value 0 and wait for delay, and write the value high to the whole port and wait another 500 milliseconds, and it is done, right? So I have to save my project. First save it and go to build solution. And if it is successfully built, you will see they'll succeed, right? 0 fault or anything. So let's say like I accidentally forget to use this CPU clock, right? Then see what will happen if I get a delay, right? Let's remove this for one. See, like it is saying a warning. If CPU is not defined utility delay, like you have used the utility delay, but the compiler doesn't know what is the clock frequency. Without a clock frequency, you can't defining a delay. Like you have to know your frequency, right? So you won't get any accurate results. Like the compiler doesn't know what is it. Could be any frequency, 8 megahertz or anything. That's the importance of having a. So if I remove this part as well and try to build it, you will see more and more errors, right? Build fail, right? Build failed because there will be some error, undefined reference to delay millisecond. So you are calling this delay millisecond function without having that library here, right? So because I remove that library, so the compiler catch it because it shows like these 4 errors. So you have to go and figure it out. Most of the time, get rid of whatever the mistakes that you have done. And so implicit declaration of function delay millisecond. So you define, call this function without having your library. So that is looking at here, the programmer definitely know, okay, I have done a mistake. I haven't included this utility delay function. So I have to use it again. So that is how you get rid of compilation errors. And also make sure you write this. If you use the delay function, make sure you defining your clock frequency, right? Otherwise, you won't get any accurate. You define the time, but you don't know your frequency, right? Time and frequency are related. Make sure you define your clock frequency accurately. Okay. So it is built again successfully. This is how you do your project. And if you want to verify what you have written, and you can simulate your code using simulation softwares. One software is called Proteus. You can search many videos in YouTube. Unfortunately, neither me or the university doesn't have a license for Proteus. In that case, we can't use the Proteus in here. So if you are interested, you can just go and see how to simulate whatever the code written in Atwell Studio in Proteus. So there are some videos you can take an idea. Basically, when you compile this, you will see some sort of like a hex file is generated. So you import that hex file to the Proteus, and then you can run your microcontroller, and it will blink the LEDs in the associated ping. There are many videos available. You can just watch them. But when we are in the university, most of the time we will build this circuit in a breadboard, and we will program it and see how it works. Using real physical hardware, that's the important part. Even when I was in New Zealand, in the labs, every student was given a development board plug into that computer USB port, so they can write this code, compile, and just using the programmer, they can burn that code, and they can see how this LED is working. Since we are now working remotely, we can't do much thing. But when I meet you physically in the laboratories, we will practice more codes. But if you are interested, you can find some kind of simulation software and see how your code works. That is also possible. And we will try to make like a project at the end of the course, like maybe assignment. So in that case, you have to build your own microcontroller system. You can program it and you can test it using real hardware. That's how you should learn rather than rely on simulations. Simulations are good, but end of the day, you have to deal with the real physical hardware. So troubleshooting and testing. So have to be some kind of hands-on experience. Otherwise, you can't work in the industry, right? You can work virtual environments like simulators, but as a technologist, you have to deal with the physical hardware. Okay, so that's the end of this session. So I recommend you to, when I upload this lecture notes, I recommend you to write this code, refer to the lecture note, and get the idea and try to write this code by yourself without looking the lecture note. And if you face any difficulty, then go and see where you have made mistakes. Then you can don't do like copy and paste like what I have done, because I have already known these things. To save some time, I just copy and paste. But get the idea, like think about you have a microcontroller, you have LEDs, and you have to first define it as a output. So this is how you write to the code in the code, and how to write these headers, defining clock. Try to do by yourself and try to build this project and see how it works. And so this is like a simple getting started type of lecture for your C code, but I hope the content I have taught is really helpful, because most of the times guys are making mistakes without knowing what they are doing in hardware. That's why I told you the use of pull-up resistors and the debouncing effects and the maximum current rating of a pin, and why those protection diodes are there, etc. Right? So you have some sort of idea what you are dealing with. Otherwise, I have seen many students failing and burning the microcontrollers many times because they don't know what they are doing, right? Okay, so if you have any questions, you can ask now before winding up the sessions. And once the recordings and lecture notes are uploaded, you can refer them and you can write this code by yourself. So any questions? Yeah, so here you have to use a programmer. So that case, we have to add the programmer, right? So if you plug a programmer and the programmer is plugged to the USB port, and then from the programmer, so you connect it to the chip, and you can use many that is not actually without the program I can't explain it, but here there's a way like device programming. Then you just burn your hex file through the programmer. Like programmer is AVR Dragon, or there are a lot of programmers available in the market. You have to buy the program, otherwise you plug into the USB port and go to here. Just once you compile it, there's a hex file generator, so you have to show the hex file to the programmer and then burn it through the programmer to the chip. That's how you program it. If you use a simulator like Proteus, you have to locate your hex file in this folder where you save it and import that hex file to the Proteus, the microcontroller, and then run it. If you use a real hardware, you just plug the programmer to the USB port and the other part to the microcontroller and go to device programming. And also you have to, actually I can't remember, sometimes you have, once you plug it, it will by default showing the programmer that you have used here. Then you pick that programmer and then go to the device programming, and then it will detect the programmer and the microcontroller itself. If the microcontroller is healthy, it is showing it is healthy. Then you can just burn the code. So any other questions? Okay, looks like no one has questions, so I wound up the session. So the lecture notes and videos will be available in a couple of hours. Thank you for joining today's lecture.